Hi everyone, and welcome to another seminar at Optimise. Our today's speaker is Dr. Hoa Bui, who is a research fellow at ARC Training Center for Transforming Maintenance through Data Science and the Curtin Center for Optimization and Decision Science. Her research area include discrete optimization, convex analysis, and graph theory, with the current focus on non-convex optimization. Hoa is also developing a platform of scheduling in the mining industry. Today, she will present on solving binary non-convex quadratic with cutting planes. Hoa, over to you.
Yeah, thank you very much for your kind introduction, and thank you very much for the invitation to give the seminar at Optima. And thank you everyone for coming to the talk as well. So my talk today is about the cutting plane method, which is broadly designed for solving a convex discrete optimization problem, and we show like how this method still converges for some non-convex framework, and by doing so we actually gain computational advantage. And throughout the talk we use the maximum diversity problem as an example how it's going to work, and then we will extend it further for more general problems. Okay, so let's start with a very simple example. So suppose like we have a map here with a lot of locations that you can choose. Here there is around 18,000 locations, and you want to locate your 50 expensive maybe equipment throughout the map, so that to minimize the effect of one equipment being taken down, for example, and which means that we try to maximize the sum distance between your selected points. At the same time, you don't want them to be too close to each other like this. You want them to be further apart for a given threshold, and the threshold is given. And this is an optimization problem. So the model of this problem is quite simple, just similar to knapsack or quadratic knapsack problems. The decision variable we're going to have is xi belong to 0, 1. So it is 1, which means that the location that you choose is selected. So and then the objective here is the sum distance of your selected location. So this here is when both x is equal. This one is equal qij, xi, xj, which means that the two locations I and j select together, then we will count the distance between them. Then this is the sum distance between your selected location. And of course, we also have you select 50 locations, and this constraint is for any paired of location, so that the distance between them is less than the threshold, then you only choose at most one of them. So this is a classical quadratics, this binary quadratics problem. So then the problem of maximizing a sum distance of your selected location is usually called maximum diversity problems. So the most classical one is maximum problem, where you select a subset of p locations among n predefined locations that maximize the sum distance between p selected points. The second second generalized or variant is capacitated, where you replace the cardinality constraint by the knapsack constraint, where we're meaning that the weighted sum of your selected location cannot exceed a given limit, or any constraint that you could think of, like the one that I have presented before. Well, for this particular problem, the way you choose the threshold actually affect the geometry of your optimal solution. As you can see here on the left-hand side here, the optimal solution, your selected point like spread apart, so that is cover the whole map. But if you don't restrict the selection to not allow them to have set the point nearby, this will tend to max out the corner. And then you will have like the equipment, like they stay close to each other. So here, this is what the optimal solution look like for the problem that we seen before. So the question is, okay, we have the model, but how do we solve this problem? Because 18,000 location is quite a large, a high dimension. In order to answer that question, let's go back to the original, the model that we are solving. So we solve a maximization of the quadratic function subject to linear constraints, and our domain decision variable is binary, and the matrix we are considering is non-negative matrix. So because the matrix is non-negative, which means that the train is positive, or at least non-negative, then the matrix Q will have positive eigenvalue. So which meaning that the Q is not negative semi-definite. So the function we are solving, maxima, is not a concave problem. So the problem we are solving mostly is actually a non-concave problem. Meaning that most of the convex technique for the technique for solving convex maximization, convex problem fails. For the maximum diversity problem, the matrix here is a distant matrix in a Euclidean space. Is where for given n location v1, vn in a Euclidean space, then the entry qij is the distance between your location. And the problem that we considered previously is also the matrix P is also have the cardinality constraint. Okay, before we go into cutting plan, let's review what are the methods that are an option for us to solve this problem QP. So currently we can think of three main approach, focusing on two main feature of QP. The first one is Q, which is nonlinear and non-convex. And the second challenge is discrete set. Here is the binary, is our decision variable is binary. So we either relax one or two, or maybe both. So the first approach is change the quadratic problem into a linear problem. So using linear reformulations. So this approach is very generic. It can apply to any quadratic problem. So this, we create new decision variable that represent the nonlinear part, and then we solve the new linear model. So in general, there are two popular formulation. The first formulation is to introduce new variable yij, which is represent xi and xj. So if we write down this function here as this, so for this formulation, meaning that we replace xij by yij. So this one is yij. So we have a new linear model with an extra, with some extra auxiliary variables. The second formulation is to replace zi by this one. So we fix I, and then we replace the whole part here by zi, which is represent the benefit that associate to xi, meaning that if you choose xi, what is the benefit that xi will bring to you? So for this formulation, the advantage of this two approach is that it's simple, it's applicable for most quadratic problem, and we can make use of linear solvers. The disadvantage is we increase the dimensions of the problem, For formulation 1, we introduce 2 and more decision variable. And formulation 2, we introduce, actually n squared, and more decision variable. So generally formulation 1 is better, but formulation 2 also introduce the big M constraint as well. So the continuous relaxation of that problem is also quite poor. So it's not only increase the dimensions, it's also increase number of constraints and the complexity of the problem. The second approach is, of course, branch and bound, because it can follow the same idea of branch and bound. We relax the integrality constraint and fixed variable, and we work with similar framework, and we solve the relaxation as to obtain the upper bound. But then it's also come with a obvious drawback. First, the solving a non-convex continuous problem is itself is an NP-hard problems, and the convex relaxation techniques are sometimes computationally expensive. For example, STP, convex relaxation technique like STP can be computationally expensive. So the third approach is actually go back to the first idea to leverage the linear solver. So we rewrite the problem into a linear form as well, but we don't increase the number of decision variable. Like, how do we rewrite the problem into linear form without increase the number of decision variable? So the third approach is outer approximation. So the idea is to approximate the whole function by a collection of linear functions. For example, you replace the quadratic function here by the collection of its tangent plane. So if the function is concave, you can see here that it can be approximated at any feasible point by its tangent plane. So, and tangent planes are linear function. But meaning that we replace a quadratic function by a polyhedral function. But the advantage of this one, before we go into how we're going to do that, then let's see the advantage of this one. The first one is that we don't increase the dimension of the problem. Okay, maybe one more, but we don't significantly increase the dimension of the problem. The cons is not mentioning how we are going to deal with that approach. It's actually require this equality. So we want to have that function, nonlinear function, to be approximated by the collection of linear function, which restrict to only concave model if you want to approximate the function everywhere. Then the function must be concave. But before we explore how this one can apply to non-concave problem of diversity problem and beyond, let's see how it's worked first. So after approximation, sometimes also called cutting plane method, cutting planes is start as follow. So now let's denote K as our feasible set with discrete with binary solutions. So our problem is maximize the quadratic function over that feasible set K. So this is actually equivalent to the following reformulation. So we create theta is a new auxiliary variable which represents the value of the function. Then we try to maximize that value, but then we need to restrict that value to the value of the true function. That's why we have this constraint. So the two problems are equivalent to each other. So from here, let's think back about the example here, where we have this function is have the tangent plane at the upper plane. So meaning that you have this function is less than or equal the tangent plane and in your feasible domain. And as where you construct the tangent plane the function, your value of the function equal the tangent plane. So which means that your function stay below this tangent plane and equal exactly the tangent plane at this point. So when we have this, when our matrix Q is negative semi-definite, the advantage of this is we will have exactly that the function Qxx equal the mean of all of the over all of the linear function that we construct as every feasible point where every x belongs to K. So we can replace in one here Qxx by mean of H that value. So constraint one when we replace by this one. And because theta less than the mean of Hy for all y over all y belong to K is equivalent to theta less or equal than all of the linear function construct at every point K in y in K at every x. So with that, we have the problem QP is equivalent to the following linear problem, this one. So, okay, we can see that now, now similar to the first approach, the problem QP is having an equivalent LB form, which have just one more auxiliary variable, but a lot more constraint. Like now, instead of growing the number of decision variable, we grow the number of constraints. Well, then the question is like, how do we solve this linear model? And then knowing that because the dimension of this model is n+1, so which means that we will have like n plus n+1 constraint, active constraint. So which means that we don't need all of these constraints y belong to K. We don't need all y. We only need some active constraint that we can put it into LP so that we can reach to the tie approximation. So how we solve LP is actually a different variant of the cutting plane method. Originally, the constraint number 2 will be dropped. And then this will generate it successively for some y belong to K, very similar to Bender decomposition method. Then there are two general approach. The first approach is to solve each LP when you add some more constraint, and then you solve each LP, relaxed LP, to obtain a new optimal solution, XK, and add the new cut into the model. And then you continue until you repeat the solution. And then we can prove that when this happens, that repeated solution is an optimal solution. Or the second approach is to think about LP as a lazy constraint approach, where you can know that there are a lot of constraints is not inactive. So we will we add cut along the branch and cut procedure, like with lazy constraint callback. So these methods will terminate at optimal solution if UK equal fxk, because theta k. The theta k is an optimal value of our relaxed LP. So that will give us an upper bound of our QP of our model. Means why fxk will give us a lower bound for our model. And when these two equal each other, then we will know that this is we reached the optimal solution. We have the approximation is now become exact. Okay, that sounds good. And then how do we deal with the non-concave problems? So when we so the first obvious thinking will be, well, we will reformulate a non-concave problem into a concave problem and apply concave technique. So we don't have to worry much about we don't have to worry much about whether the methods converge or not. So indeed, we having the bilinear binary problem has an equivalent concave reformulation. This is because of this property. because xi belong to 0 or 1, so we always have xi squared equal xi for every I. Then we can then the function qxx here equal this one, because this one is 0, and rho can be any real value. So when that happens, we can take xi squared and put it into the quadratic function. Then we have this function, and then we have a linear function. So this matrix means that you just change the diagonal of the matrix Q by take minus rho. And then when rho is large enough, in particular larger than the largest eigenvalue of matrix Q, then what it does is then the matrix Q rho here will be negative semi-definite, because when you take the diagonal of all of the diagonal by rho, then all of the eigenvalue will be minus rho. So when you take rho is the largest eigenvalue, then that's the large. After you take you change a diagonal, the largest eigenvalue will be 0. So we have a negative semi-definite matrix. And we have these two models are equivalent to each other, while this model is concave, have concave objective. So yeah, so we have an equivalent concave reformulation. And maybe you think, okay, maybe compute the largest eigenvalue of Q is difficult. No, it's not necessary to be a large eigenvalue. You can take rho as a max rho sum of Q, and then we will have that Q rho is negative semi-definite. Okay, it's too good to be true. So why people don't do that? It turned out that concave reformulation is not a good idea. The reason for that is this will significantly weaken the cuts. If we apply cutting plan for this new model, it will significantly weaken the cut. So to have a mathematical way to support that claim, let's look at the cutting plan generate for two reformulations with rho 1 and rho 2. So we reformulate the problem with two parameters, rho 1 and rho 2. Both of them can be positive or negative. And here are the tangent plan generate for two models. And then we can show that the tangent plan here at x here is the binary point. For the smaller parameter will be smaller than the tangent plan construct for the larger rho, the reformulation with larger rho, meaning that the cut generated for a reformulation with smaller rho will be tighter than the cut generated for the model with larger rho. So which means that when you choose rho is the largest eigenvalue of the matrix, that value can maybe too large, and then that's why it's not a good idea. And this inequality is strict because the equalities hold only when rho 1 and rho 2 equal each other. So meaning that they strictly so this one is strictly tighter than this one. So what this result tell us? The first observation is concave reformulation step will weaken the cut, and the numerical experiment in various survey paper have showed that the cutting plan methods with concave reformulation usually even weaker than standard linear reformulation. So it's not really referable. But what missing is now even for a concave problem, in order to improve the cutting plan, maybe we have to think about to de-convex the problem, because we going to use a smaller rho, maybe negative rho, to make the problem less convex, and then you apply the cutting plan. The cutting plan will be tighter. So in order to, okay, so we start with how do we convexify the problem, how the convexify the problem. Now we conclude that, okay, maybe we even make the problem not convex. Then what is the sweet spot in the middle? In other words, what is the condition that make the cutting plane converge for non-convex setting? Okay, we need a condition that weaker than convex for us to guarantee the convergence of the cutting plane methods. So if we look at the conversion of the cutting plane methods, what are the properties that make the methods converge? So the first property is the cut that you add doesn't remove optimal solution. It's not feasible optimal solution. So meaning that this condition holds. This condition means that the tangent plane that you construct at xk doesn't exclude the solution x star when x star is the optimal solution, x star at x star. Well, before and here is the second condition is where the tangent plane you construct at xk must support the function f at xk. So this one so for these two condition, we can see that the first condition always holds for free because h is a tangent plane. It's always support the function at xk. So, and for the first condition, the cut could exclude feasible solutions. And we don't care about feasible solutions. And there's no need for concavity assumption to achieve the first condition. But the question is how? How do we check the first condition without knowing where the x star is? So we can replace the first condition by this condition, meaning that now we can see here this is actually x star. So now we replace x star by x, where we can replace x star by x, where all of the value of the function f, when the value function f at x is bigger than your current solution, candidate solution, then you have to make sure that your cutting plane construct at xk doesn't exclude that solution. So we don't know where x star is, but we can make all of the solution that is higher than the current solution is feasible. So this is actually similar to quasi-convexity, not convexity, quasi-convexity. So what the convex look like? So this is for convex problem for all x belong to k. So now we don't need to be this one to hold for all x belong to k. We only need for this x where x belong to k, so that the value of function f at x is bigger than the value of the function f at xk. But bad news is for a quadratic function, quasi-convex is equivalent to convex. So we need one more step to achieve a weaker condition. So where we consider a directional convexity. So what that means is we take, for example, your x case is here, and then your x is here, and then we draw a line between x and xk, and then we consider a one-dimensional function that embedded into this line, x and xk. So because this is a quadratic function, the function that embedded into the direction x and xk is one-dimensional quadratic function, which either convex or concave. So we can actually tell that, okay, x and xk, what is the direction? What is the convexity property of the function along that direction? Okay, so how we book all of this idea into practice. So we prove that when the function q, when the matrix q had exactly one positive eigenvalue, meaning that it's not, then given a 2 point x and y, then if we have a direction, new direction, axis direction, such that q x z bigger than 0, which means this is a strictly convex direction, then if x and y, x tag y is orthogonal to QZ, then x tag y is a concave direction. So meaning that the tangent plane construct as y admit x is a feasible solution. Okay, so we can actually characterize a convex direction of a quadratic function. And then we can answer the next question is, how do we know that at the tangent plane that you construct y here, how do I know that x, how will you know x star minus y is a concave direction? And so your tangent, the cut that you generate is valid. So that can be characterized by a similarly a assistant of a vector, so that this one hold. This condition is actually weaker than this condition. So this condition is equal 0. This condition is just less or equal to 0. Okay, let's move on with technicality. So this one is we use the property of the optimal solution is that this one, meaning that when x star is the optimal solution and y is not and y is a feasible solution, then the value of function at x star is bigger than the value of the function as y. That's why we have this one. And then we also have this one because of the property here. The assumption, then the assistant of z is given when z is the point in the middle between w and x star plus y. So that's why x star take y is a convex direction. So then from here, we can prove that the cutting plane lies directly for this model converges without a convexity assumption, concavity assumption on the objective function, meaning that we can choose rho equals 0. So instead of choosing rho is the larger eigenvalue of Q, which is very large, we choose rho equals 0. And then the cutting plane method still converges to optimal solution QP. This is thanks to the fact that we can prove that whenever you solve the repeated LP to optimal solution, we can show the assistant of the vector V, vector W here, and the cutting plane construct at that new optimal solution is always valid. So okay, so what is the takeaway here? The takeaway here is when we need concavity to assumption for the cutting plane, for the outer approximation to be successfully approximate the whole function by a collection of a linear function. But for the cutting plane methods to work, we only construct the tangent plane at certain point. And what we need is we just need to make sure that the tangent plane that you construct at those points doesn't exclude optimal solution. The method still accepts. Okay, so let's test the idea on the capacitated diversity problem that we mentioned from the beginning of the talk, where we try to maximize the quadratic function with the the knapsack constraint, and our decision variable is binary. So we test some methods against the best known exact methods for this class of the problem. So you can see a review paper here. They discuss about different heuristic and exact methods for solving this problem. So at the moment, the best known exact methods is a Clover linearization. And we also test with the quadratic programming solver in recent Groby on the public data set, public in here. So let's first see the performance of the cutting plane methods. So all of the location, all of the instances with the dimension with 500 locations is used, and then we generate weight for the capacity constraint at the standard test for this problem. As you can see here that the runtime on average is less than 1 second. the number of cut required is less than 5 iteration. So meaning that each cut is very very strong. So the dimension of the problem is 500, but then the cut you require to add is only the largest one is only 7. For the larger data set where we have more than 1,000 locations, the performance is still very consistent, where we also converge on average less than 1 second. So we test the performance with other methods. So here we have repeated LP. ILP is the cutting plane methods that I introduced during the talk. The 2 methods are our methods as well, using lazy the second approach we use is to add the cut along the approximate along the branch and cut procedure, which I didn't introduce here. But then just look at the repeated ILP and the Glover linearization and the quadratic programming. So as you can see, all of these cutting plane methods with the new idea that we apply directly for the non-concave model instead of concave model, then it converges much quicker in mostly less than 1 second, while the other standard methods take much longer time to solve they're just half of the instances. Yep. So this is the table for numerical experiment. Interestingly, when we run this example, we thought that okay, false cardinality is actually should be the strongest one, because we don't create new LP model, but we just keep one single LP model and then ILP model, and then we solve them. We add the cut along the search tree. But it turned out that repeated ILP is actually faster, is because when we each of the LP model is not expensive to solve, and the quality of the cut we get after we finish one solve is actually strong. That's why we just require 7 iterations in general, which means that we only solve 7 times. So it's much the cuts are stronger than false cardinality. So the next one is the maximum diversity problem, where instead of having a cardinality constraint, the NAFSA constraint, we have a cardinality constraint. So for this problem, we have one advantage, is the equality constraint, meaning that the function here is embedded into n-1 subspace. So we can make use of it. So we can show that instead of keeping rho equals 0, we can choose rho as a second largest eigenvalue of Q, which is negative. Then when the first added cut is valid, which we can decide to have that happens, then the cutting plane methods applied to the reformulation model convert to optimal solution as well. So instead of applying to DSP with rho equals 0, we reformulate that one more time to get a smaller rho, and then we have a stronger cut. So when we apply for rho is the second largest eigenvalue, so we have a smaller rho. So for apply the cutting plane without reformulation, rho is 0. Apply after reformulation, rho is negative, so it's smaller rho. Then we can see that this is a fewer iteration and faster convergence, so we can solve all of these instances quicker. So the last one before I conclude is a extension to a quadratic fractional problem. It's not a quadratic problems. To demonstrate the idea we mentioned before, that okay, to have the cutting plane to converge, maybe we only need quasi-convexity. So when Q is a distance matrix in the Euclidean space, then the function f is pseudo-concave. Then the cutting plane approach still converges to an optimal solution of this problem. And for that, we just need to apply the cutting plane directly to this model. And then you can see here that for this quadratic fractional problems, the cutting plane converges very fast to the optimal solution with very few iterations. So just to demonstrate that, okay, applying to non-concave model actually quite an advantage for us. Okay, so the conclusion is for cutting plane methods, concave and convex structure can guarantee convergence, but it can adversely affect the convergence speed. And maybe for concave problem, we think about deconcave the problem to improve the computational efficiency. So the reference of the talk is for the first paper, but I did use some other paper after as well, for example, and numerical experiment. Thank you very much for your attention.